Okay, so let me close this down a little bit. Hopefully people can see that. Someone can tell me in the chat that they can see it. That looks like a yes. Okay, yes, so I'm going to talk to you about these interesting things called metasurfaces that some of you may have heard about, maybe not, but I'll explain what they are. And I'll tell you about the work I've been doing on using them for beam steering. And this is mainly for photonic applications, but some of the concepts here span the whole of the electromagnetic spectrum, so you can use them in many different wavelength frequency ranges. Yeah, so this is what I'm going to talk about. I'm going to introduce metasurfaces, explain what they are, and then the particular thing that I'm looking at today is what's called tunable metasurfaces, where you control their parameters. And then again, we'll look at another specific type of metasurface called the reflect array that allows you to do various kinds of beam steering applications. And then I'll sum things up at the end. Let me switch my pointer on. Okay. Yeah, so these things, metasurfaces, they've got a whole range of applications across the whole of the electromagnetic spectrum, but also in other fields of physics as well, acoustics, mechanics. A lot of these concepts are very general. And so they're sort of interesting from that point of view too. There's many different types of metasurfaces, but generally what they are is thin structures. So that's thin in terms of a wavelength. They're normally two-dimensionally periodic, and they've typically got sub-wavelength periodicity. So these features are quite small normally relative to a wavelength. And how they're formed is from what we call meta-atoms. So individual, often resonant structures that you can control the phase and amplitude of these structures. And that allows you to do all sorts of interesting, perform interesting functions, such as, controlling the shape of a wavefront or steering a beam in a particular direction. So these things, metasurfaces, they're actually a subset of a larger sort of field, if you like, known as metamaterials, which again, some of you may have heard about. One of the big problems with metamaterials, they're typically three-dimensional structures, three-dimensionally periodic structures, and that can be really challenging to fabricate. So the big advantage of metasurfaces is, in principle, they're not too different from, making PCBs or making silicon chips that you might find in your phone and things like that. So they're very amenable to fabrication. So I'm going to show you some examples to do with photonics. And this is a sort of starting point just to introduce simple metasurfaces, if you like. If any of you have, studied anything like, microwave antennas or things like that, they're not too far removed from an antenna. So this is a typical structure. And the idea of this whole metamaterial metasurface is, what happens is you can give pretty basic materials, in this case, gold, aluminium oxide, and gold. You can give this structure properties that aren't available to those individual materials. In this case, I'm talking about electromagnetic behavior. And that's why this term meta gets used, because
Hello, everybody. We predicted this may happen. There seems to be some internet connectivity issues towards Bristol. So this is Dan Warren, one of the non-Bristol speakers.
Inductance happening within the structure simultaneously. But what happens if you design this structure correctly, then you can get this type of unusual behavior. So here we're plotting what's called the effective refractive index of this material versus wavelength. And we're looking at the real and imaginary parts of it. So normally for a normal material, the real part of the refractive index must always be greater than 0, and the imaginary part must also be greater than 0. But here we've generated, across this particular range of wavelengths, we've generated this region of negative effective index. So that's, there are all sorts of applications. Once you have some negative refractive index, there's all sorts of things you can do with it. One of the most famous examples is what's called a flat lens, where normally a lens has to be curved in order to give it lens behavior. But this negative index allows you to design these kind of things that have all sorts of potential applications. And I started studying this stuff quite a long time ago in 2012 with one of my first PhD students. This is after he finished his PhD. He's an academic in China in Dalian University of Technology. So that was kind of interesting in its own right. We didn't make any of these things. Making these things is the difficult part. Let me get to my next slide. Okay, yeah, so this is the tunable aspect of things, is that there's these wonderful materials called Chalcogenide Glasses, and they have this very unusual property that they're basically stable materials that have two possible phase states that you can switch between. And they're called, there's a general class of materials called phase change materials. You know, all materials can change their phase. You know, water can freeze, it can evaporate, and these are essentially what are known as phase changes. But here's what's interesting about these particular types of glasses is you can radically change the electromagnetic properties of them. So this is the dielectric constant, the real part, and the imaginary part. So when it changes from these two states, amorphous and crystalline, you can go from a dielectric constant of about 15, you can switch it up to about 35. So a huge change in its electromagnetic behavior, if you like. Whilst the imaginary part, which tells you about how much losses you've got in these structures, stays very low. So you're not going to do much absorption, but you can radically change basically the phase response of these materials, or if you like, the electrical length of them is another way of thinking about what's going on here. And the way we can change these phases, you need to put heat energy into the system. And so you can do that generally in two ways. You can use dual heating in thin wires, put a pulse of current in a wire, will generate heat and you can change the state. Or a lot of people use laser pulses. The most elegant approach is with, electrical switching, because again, that maps into the whole idea of silicon chips and PCBs and things like that. The other really nice thing about these materials is they're very well established in a commercial sense. You may not know, but this materials, chalcogenide glasses, are how rewritable DVDs work. A laser basically changes the state and it can flip the state back again in order to rewrite the DVD again. And Intel have also developed that when you change these states, not only do the optical properties change, but also the electrical properties change too. And that means you can actually develop a whole new type of random access memory. And Intel have developed one of the first types that's available commercially. It's called Optane. So the concept of the material works very well. And yeah, again, a number of years ago, we started working with this researcher in Exeter University who knows how to make these materials. And we started to explore what's possible in terms of tunability. Yeah, so this is what we came up with. We did the simple thing first, take the structures that we were studying anyway, but now sandwich one of these chalcogenide glasses. There's a whole zoo of these glasses you can choose from. This is one of the more standard ones. This is germanium antimony telluride, and you can sort of pick and choose the various numbers of these atoms that go to make up the particular molecule you're working with. Okay, let's keep going. Yeah, so this is the kind of behavior you can then get. You can generate your negative effective index like we had before in one state, crystalline, but you can switch it now to amorphous into another state, whilst maintaining reasonably low losses. The losses aren't great here, but they're low enough for potential applications. And we started out here in these long wavelengths. There's whole set of applications in things like gas sensing and a few communications examples out here at these long wavelengths. But that was just to establish that we could make these things, at least make them work, not physically make them. So that's this. Then it's moving on to reflect arrays. that are sort of like associated with metasurfaces. And I should acknowledge the great help from an academic who was here at Bristol when we started this work, Machet Clem, who had been working on reflector rays. I'd been working on these tunable materials, so we kind of worked together to develop this structure. So here you can see again, we've got this layer of chalcogenide glass, and this is the kind of level of detail you need to use if you're going to make one of these structures. You need to coat the glass in what's called indium tin oxide. We've got a silica layer here, and then a silicon substrate at the bottom. And here's our second metal layer, aluminium on the top. And what we're doing here is we're basically changing the resonant phase response. These are the meta atoms that I mentioned earlier. And we're changing the phase response of each one of these meta atoms such that when a plane wave comes in here, it either sees a phase gradient or it doesn't see a phase gradient. It's essentially like you could have the same behavior by mechanically tilting this structure, but we're effectively mechanically tilting it, but we're doing it electronically by changing the phase delays across this surface. So this is the behavior you can get in the crystalline state. Essentially, you get what's called specular reflection, so the light will come straight in and back out again. But when you switch to the amorphous state, we get these phase delays between the meta atoms, and then the plane wave coming in effectively thinks it's getting delayed in such a way that it comes out at a given angle. So we published a paper a few years ago with Exeter University. David Wright is the head of the research group in Exeter, and we finally actually made one of these things. So that's the really difficult part. And that's what Exeter are sort of world leaders at, is doing the fabrication stage. Here's another little bit of information on that design phase. So here we're plotting the reflection phase of a given meta atom versus the width of the aluminium strip within the meta atom, and in the two states. You can see when the width is about whatever we are here, 150 nanometers, we can switch the phase 100 down to 0. We choose 210, we can stay around about 100, but now switch it down to minus 100, and so on for each one of these points. So basically in the crystalline state, we have essentially a flat phase front, but in the amorphous state, we can create a steep phase gradient that essentially that will deflect the beam. So, okay, let's keep going. Yeah, and so this is what they look like when you make these things. This is a standard microscope image, 10 micron scale bar. Then we go into an SEM, scanning electron microscope, to zoom in even further. Here's the aluminium strips, 1 micron scale bar. You can see they're not perfectly straight, but that's the kind of behavior you get in these devices. So let's keep, oh, here we go. Yeah, so this is now, so the job in Bristol was to simulate these things, design them and measure them. They were made in Exeter. And we used what's called hot plate tuning. So this is, you can tune from one state to the other in one direction just by putting the device on a hot plate. But once you've done that change, you can't switch it back again because basically you need very high temperature, short current pulses or heat pulses, and hot plates can't achieve that. But anyway, we're looking at simulated results here at the top, measured results at the bottom. In the two states, we've got the amorphous state here and the crystalline state. So in the crystalline state, you can see we're basically plotting reflected angle. So the reflected angle is 0 across a whole range of wavelengths. That's the other thing to point out, is these devices are generally very broadband. So it doesn't matter what the wavelength is that's coming in, you can reflect it back out at 0 degrees. And here's the measurement, agreeing pretty well. These measurements aren't easy, but we think that's pretty good agreement. And then you switch to amorphous state, and we're steering off to an angle of somewhere around 30 degrees in simulation, and we're getting pretty similar behavior in the measured case. So we were really happy to achieve those kind of results. So that's it from me, basically. Let me just sum up. So hopefully I've shown you these tunable metasurfaces. They're kind of interesting for all sorts of applications. Things that I'm particularly interested in is Lidar. You know, Lidar is still an unsolved problem at the moment. Most cars that, you know, autonomous cars essentially have spinning lasers on the top of them that cost probably more than the car. And so there's a huge research effort going into low-cost Lidar. And I think these kind of metasurfaces might play a role there. The other thing we're thinking about is on-chip communications. You can use mirrors and these tunable mirrors to achieve that, and maybe even chip-to-chip communications as well. The other thing I'm working on is we're developing, oh yeah, this is the really big step, is that we're gonna electrically switch these things and reversibly switch them. So by simply putting electrical pulse into a wire grid, we can selectively tune these materials so that we can tune essentially multiple beams in multiple directions. We're also exploring other tuning mechanisms. Some of you may have been here yesterday. So this is my PhD student, Yutian Zhang. He gave this talk about optically controlled microwave switches, where we illuminate silicon. And when you illuminate silicon with particular wavelengths of light, you can get these types of tuning behaviors. And the other thing we're exploring is the use of these ideas in the terahertz range. We're developing a new test bed from 100 gigahertz to 3 terahertz, such that we can do these measurements in-house. And we think some of these ideas can get used in reconfigurable intelligence surfaces, where this kind of steering, you have to steer things at very high speed. Okay, that's it from me. I shall, I might as well stop sharing to begin with. And let's see if there's any questions from anyone. You can either switch your camera on and ask the question live, or I can have a look in the chat and we can take things from there. Oh, someone's asked a question. So this is Christopher Christie. Are you also researching the use of gallium nitride for 5G and photonic solutions? Yeah, I mean, we've got a whole host of projects running in this general area of sort of like electromagnetic devices and which materials are best for which applications. And gallium nitride is a really interesting material. In fact, we have a really nice EPSRC project running at the moment called Glimmer, with Krishna Balram is the PI of that project, where we're using gallium nitride to develop new types of surface acoustic wave filters. But yeah, gallium nitride is a wonderfully functional material. It's, you know, you can make transistors in it, you can make lasers from it, it's piezoelectric. So there's all sorts, and it's now available in foundries. So, you know, you can make millions of these chips for almost the same price as silicon chips. And so we're looking to exploit that kind of behavior. I think the main thing in all these spaces, it's a good idea to choose a material that's pretty well established, you know. So that's why I like these Chalcogenide glasses, because they're industrially perfectly usable, they're low cost, and so it's nice to explore them. Okay, any other questions from anyone? Okay, right. So I think let's move on to the next speaker.